So let me continue. Before I start, any questions to the first 2 hours? Okay, so I'm a little bit slow with the definition of the vertex algebra because I don't want it to come out of the blue. So far in the last 2 lectures I talked about affine Lie superalgebras and how one can naturally encode information about the affine Lie superalgebra in generating series, which we called fields. The name fields comes from quantum field in physics. And we computed a little bit of their structure. We saw that in the commutator of 2 fields, so the main computation we did last 2 lectures was we chose 2 elements of our Lie algebra, then the commutator is a 3rd element. I didn't give it an extra letter. So to every element in the Lie algebra, we can associate a field denoted by the capital letter, which is the sum over all these modes, and then this formal power series. Also note that this -1 is just for convenience, so that formulas are nice. Right? One could have neglected it, but it would just make form expressions a little less pleasant. And then we computed this commutator of the 2, and we saw the formal delta distribution and its derivative appeared. So in particular, if I multiply this commutator by z minus w squared, then it vanishes. It has this somehow nice property. This property will be a key ingredient in the definition of a vertex algebra. So what I want to do for the next 2 hours is I want to introduce first another product called normally ordered product. Then I will give you the definition of a vertex algebra. And then I'll give you, you will see in the definition this property is key. So I'll talk a little bit about this definition and how you can think differently about it. And then I'll give you a bunch of examples, and that will conclude the first day. And maybe I will not even get that far. Okay, so first let's start with the normally ordered product. So remember for our affine Lie algebra, the module on which it acts was generated by a cyclic vector, which I will always call vacuum vector. And this vector has the property that a mode annihilates it if the index is non-negative. So somehow one would like to define a product where all modes that are positive, that annihilate the generating vector, are moved to the right, so that this product is better behaved on the module. And that's the normally ordered product. So we take a field A as before, and now we define its positive and negative part by the by restricting to non-negative powers, respectively negative powers of z. The summation is a little bit funny just because of this convention that you have a n z to the negative n minus 1. So a plus are the non-negative powers of z in the field, and a minus the negative ones. And then one defines the normally ordered product. The normally ordered product is denoted by the symbol and it is the positive part of A times B, and then the negative part So here I always define it for homogeneous fields. That means the fields are either odd or even, but not mixed. Just so all it means is we write down the field A into its sum over the positive powers of Z. We keep them as before, but the negative powers of the part that comes with the negative powers of Z is moved to the right of the field B. And if both B and A are odd fields, we have to introduce an additional minus sign just because of the of changing the order. And now this has the property negative A minus, right? It's it means the AN modes are exactly those that annihilate the vacuum vector. So what you see is if I take this normally ordered product and let it act on the generating vector of our, this is now just in the affine case, then the normally ordered product is just this one on acting on that. So okay, and now why does so the philosophy is those that annihilate that have the tendency to annihilate are moved to the right of those that create states. Okay, and now let's do this in our example and see. The claim is that the normally ordered product makes our product of fields somehow nicer in the sense that we don't have to deal with formal delta distributions anymore. So let's see how that appears.
Why is that normally ordered? Never mind, I understand.
That's yeah. So normally ordered is in physics is the right in. Let's just recall a little bit of physics terminology. The generating vector is called a vacuum vector, and then we have annihilation and creation operators, where xn with n annihilating the vacuum is an annihilation operators, and the others create states. So they are creation operators, and these are good names, of course. And the normally ordered product is the product that makes the action as good as possible in the sense that first you have act with everything that annihilates, and then with the ones that create. Okay, let's just see how this works in our case of our Lie algebra again. So let's recall. We take our fields x and y again. And let's now look at the product of x with y, the honest product. Now, of course, the product I can write, x I can write as its positive part plus its negative part. And now I want to have the normal ordered product in there. So here I already have the first term. Now I would like to have this one as well. So I add it and subtract it again. So here I add exactly what I need so that these two summands combine to the normally ordered product. And now subtracting it again, what do I see? Well, here I have x minus times y minus 1 to the parity y times x minus. So here I exactly have the commutator of the two. So we see, the normal ordered product makes exactly the ordinary product of two fields into, I can write it as the normally ordered product of the two fields plus the commutator of the just the negative part with the second field y. And that's kind of nice because now I can redo the computation of last lecture, and I will do that. And instead of the delta distribution, we get kind of half the delta distribution, which is much nicer, as you will see in a few minutes. So let's compute this commutator. And
Is it true that the parity of big X will be the same as the parity of the little x that you hit?
I should have said this. So I got a few people asking me. So I only introduced the parity of the Lie superalgebra, not its affinization, but this variable t just is even, and so that means each xn has the same parity as x, and so in particular the field x of z has each mode has the same parity as x, and so the field has the same parity as x, and then this notation makes sense. So I absolutely should have said that earlier. Okay, so I just plug in what this is. So here, the only difference to last lecture is here now I only sum over non-negative integers. The summation for y stays the same as before. Here the commutator of the two, and then I can plug in the expression. Let me use exactly the convention I used here, that I give the commutator of x and y the name v, so that I okay. And now I again want to express this in terms of a field. So I would like to, so I set L to be equal to n plus m. So this means here this m I write as m. I add an n, and then I have to subtract it again. And then we get here the sum over L and Z, or VLW minus L minus 1. So the field associated to V, to the vector V. And we still have here the sum Z to the negative n minus 1, and the W is to the n, which is in fact exactly the same thing as before, just that we sum over a different region. And then here we have the condition that n is equal to m, minus m. So the sum becomes just and now we see this first expression is just the field associated to the element v in the variable w. And what is the sum over non-negative integers? W over z to the n times 1 over z. Well, what is the sum n over the non-negative integers of w over z to the n? That's a geometric series if w and converges if w over z is less than 1, right? So that's very nice. So let's write this maybe down here. We have here 1 over z and this is the same as 1 over z, 1 over 1 minus w over z if so this means this expression is the expansion of 1 over z minus w in the region w has an absolute value less than z. And so this means we write it like this. and maybe we'll, to be completely precise, we will give it an index, for example, W over Z, indicating that we mean the expansion of this expression in the region where this is less than 1.
This is the first time where you actually don't think of those as just formal variables.
That's the first time, exactly. In particular, now, while I've, we should discuss your comment in a second. Let me just first complete. Well, this sum is just the derivative with respect to W of this sum. So that means the derivative with respect to W I can just take, and so what is this? It's Z minus W squared, and the expansion of this in the region where W over Z is again less than 1. So let's just, to be complete, introduce this notation. W over Z is the expansion of in the corresponding region. All right, and now you see what does this mean? We have here the product. So the product of the two fields is the normal ordered product plus what we exactly computed. Well, what we exactly computed is something expressed just in terms of a single field, or actually just a scalar. In particular, this one acting on, for example, on the vacuum. This one acting on the vacuum will give us a Taylor series in W. So we get here, acting just on the vacuum will give us a Taylor series in W with coefficients, polynomials, and Z minus W inverse. Something kind of nice, right? While what about the normal ordered product? It has the property that this one annihilates the vacuum, and here only the these expressions. This one, the positive part, now will give us a power series in Z inverse, and here, well, you can figure it out. Somehow it nicely divides up the product in portions that act nicely on the states of our module.
Can you explain a little bit more, or maybe just write what you were saying?
Sure. So yeah, Taylor series is just formal power series in Z.
Like in W, you won't get negative powers? Does that sound something?
Well,
Okay.
yeah.
I'm bored now.
Yeah, good.
After the vacuum, I want this to be 0.
Yeah, let's just think about it. We have we can now we have distributed our product into two pieces, this one and this one, and now what you can do is you can for example, look at the normal ordered product. How does it act on your vacuum? Well, this becomes just the and if you how did I define minus? All right, since the negative part annihilates it, and in fact I can even, this y also distributes, is the positive and the negative part. So somehow the normal ordered product is just this one, right? And since the positive part is a power series just in Z inverse, so then this expression becomes, right, it just becomes a power series in Z and W inverse. And now you can look at the other parts, and here this one, what will it give you? Again, it's just the action of V plus. So maybe I will not write it down now.
No, can you please write it down? So I
Okay,
understand.
sure. So we have divided the product up into these pieces. We have computed this one. And now I can use again that just the negative part annihilates the vacuum so that this collapses to the sum again.
What was the point of all that?
It was actually just a side remark, which you wanted me to expand on.
No, but you were saying that this was somehow helping you to compute something, or is it explaining why the normal order product was...
Right. So there are 2 points of it. First of all, if I introduce this normally ordered product, all of a sudden the product of the two fields becomes a very nice expression, namely the normal ordered product plus this.
Yeah, but what is nice about this expression? That's what I don't understand.
What is nice about it is that I will now next define a vertex algebra, and then we will see how these types of product nicely encode information about both commutativity and associativity of the products. So I would say wait another 20 minutes, and you'll see more on this. Okay. Let's go on.
But so far we're just treating the variable ZW formally when we act on the vector.
Yeah, and we for a very, very long time, actually one treats these variables as long as one can formally, and only once you want to go to tensor category or to correlation functions, you need to treat them as complex variables. Only at the very end, so maybe only starting Wednesday or Thursday, we will think about them differently. But of course, it's very important to eventually treat them differently. So let me introduce one general lemma, which I will not prove because I'm slower than expected. So I take a bunch of fields A, B, and C1 up to Cn minus 1, and then the two statements are equivalent. And this equivalence is very nicely illustrated by the computations I've done so far. So the first one is about the commutator of the field A and B. Well, we have seen in our Lie algebra case, the commutator is expressed in terms of delta distributions. And in general, if I can write this commutator of these two fields as a sum, where the coefficients here are these n-1 n fields, these n fields, and the coefficients are derivatives of the formal delta distribution. Then I can do this if and only if I can write the product of the fields in a form as illustrated just above, where I replace the derivatives by one second. I forgot a j factorial somewhere. Ah, right. Here I need a j factorial, and also this, the other way around. And here I have to keep track of the regions in which I expand. They are opposite to each other. And checking that this is correct is then, well, it is explicitly, it's an explicit computation that I now decided not to do. And initially I wanted to do this. So the point is we have two equivalent ways. We can either compute the commutator of two fields, then formal delta distributions will appear, or equivalently we can write it, look at the product of the two fields and minus its normally ordered product, and then instead of delta distributions we will only do half the sum, and half the sum will correspond to the expansions of powers of z minus w to some negative power in these two regions. Right, it's w minus z. Thank you. Okay. So in particular, if one has a field that has this property, then if I multiply it by z minus w to this capital N, then all these derivatives of the formal delta distribution will be annihilated by this. So this means these fields A and B will have the property that multiplied by z minus w to the power n here will vanish. And this is the property that's called locality, and that is the key property in the definition of a vertex algebra, which I will now finally give. So I can write the commutator in this form.
What does fields mean?
A field is a formal power series with coefficients, endomorphisms on this one.
Oh, okay.
Right. So.
But didn't you say that you always have this part 1 with just 2 terms?
For the affine algebra, right. So I.
Are we saying that?
So this is the x of z and y of w were examples of fields, and this is now a statement for general fields.
But is the statement somehow just that it's a finite sum, that does it always have an expansion like this, except that maybe it goes up to
Yeah,
infinity?
absolutely.
It's the same CJs that are appearing in the three statements.
The same CJs appear here, and it's important that it's a finite sum. So the finite sum is definitely important.
And so it's the only difference, G is infinite dimensional here, right? So you did a computation for a Lie algebra.
Yeah.
Showed that we got 2 terms.
Right. So.
But now you're saying for general V, and is it because V is infinite dimensional that there's a difference? Because endomorphisms of V form.
Yeah. So the simplest example of a vertex algebra is an affine vertex algebra coming from an affine Lie algebra, and I demonstrated everything so far in that example. But however, the general vertex algebra will have simply fields that satisfy a certain property that I will write now down, and this lemma holds for in the general setting of fields. The underlying vector space is always infinite dimensional. So right, because of already for the affine vertex algebra, it's this vacuum Verma module. I think you are still unhappy.
Well, I think the answer to Jürgen's question, or someone else's question also, is that you use the word field to mean two different things. First time you said field meant a certain thing which you promote a Lie algebra element to.
Right, yeah. Mm-hmm.
And now you're using field in a sense which includes that, but includes also a lot of other
Mm-hmm.
things.
Where they vary from.
Yeah,
Those vary over the end.
So a field on a vector space is a formal power series with coefficients, endomorphisms on V, and the example we always had was V was this what I called this VKG, and that's probably the confusion.
No, but the ANs are more special in that example. ANs are not general in that example.
Also, they are not general. Absolutely. And they are not right. And example V, right, absolutely, and very special fields. Absolutely.
But if V is finite dimensional, are we saying there's only finite many terms in the sum?
The only vertex algebra that is finite dimensional is trivial. So there are V finite dimensional will never appear.
No, I'm saying here in this definition now, AN is completely arbitrary. There's no relation between the ANs for varying n. But what was before was that AN was xn, which means x times t to the n. So there's a strong correlation between the ANs.
Yeah, but I mean, the interesting case would be, take a fine Lie algebra, but V would be just some representation of it, according to the definition we have this morning. Would we then have, not just two terms, but finitely many terms, depending on some other dimension of that representation?
So
that's what I mean with finite dimension.
yeah.
In the beginning,
It's a
because
fine Lie algebra, but not the trivial representation, but just some representation.
So I hope all your questions become clear fairly soon. It's
But we're just trying to forget this morning and pay attention to this definition.
absolutely, yeah. So this is the definition of a field, and we will come to the notion of some kind of dimension very soon, and that will give us information about what this n is. Okay.
Could I ask one quick physics question?
Yes.
So the negative modes annihilate the vacuum, annihilation operator. Is there an intuitive way why these negative powers we would want to associate them with annihilation operators?
Can you say it again? What?
So we have the negative,
Yeah.
the x negative which kills the vacuum.
Mhm.
They correspond to annihilation operators in
Mhm.
physics. Is there an intuitive reason why these negative powers of z, or positive powers of z, we would want them to correspond to annihilation operators?
You mean this funny convention that it's ANZ to the minus n minus 1, or?
No, so I just mean because we had these xn
Mhm.
on the vacuum is 0
Mhm.
when n is positive.
Mhm.
Why do we want positive powers of t or non-negative powers of t to kill the vacuum?
Precisely because you then get such a nice product of fields. So what you want is you want products of fields to be up to this normal ordered product, polynomials in z minus w inverse with coefficients fields again. That is simply structurally a very nice property. You can see if we maybe at some point define some kind of pairing between modules, then this product will translate to certain functions, and then it will be meromorphic functions with bounded poles and in Z minus W. So this product exactly gives you some kind of nice pairing then also of fields.
I have somehow like completely irrelevant question. Is this supposed to remind me of the hyperfunction description of delta function? Is that what's going on with Z smaller than W and then Z bigger than W?
What do you mean with hyper?
Like distributions that can be described sometimes like function of upper half plane, function of lower half plane, which agree away from the singularities of distribution.
Yeah, it's definitely not supposed to remind you, but it could. But so it is correct that it reminds you of, but it's maybe in this context not the correct thing to think of. Okay, let me finally define a vertex algebra. The definition has two pieces. The data will be the vector space we always had. So a vector superspace, and let me write over C, though just because I will work over the complex numbers the whole time. A distinguished vector called a vacuum. A translation operator. And most importantly, an assignment that assigns every vector a field. So we take a vector in our vector space and we get a corresponding field, which we will usually write as V sub n z to the negative 1 minus n. And so we have all this whole data we've already seen, except I have not given the explicit prescription here, and we haven't seen the translation operator yet, just because it's less important.
Okay, sorry. It keeps bothering me that things are not symmetric in Z and W. So I'm happy when you put a delta function next to it. So then Cj of W is fine. But in the second part, when you write B times A,
I'm sorry, I completely confused myself. I wanted to write a Z here.
okay.
I wanted it to be completely symmetric. Yeah, I'm sorry. It's good that you notice this. Okay, what are the axioms? So the field associated to the vacuum vector is just the identity operator on V. So, if a field acts on a vacuum, we want to get the original vector V back, and then plus something that's somehow subleading. So that means it only has positive powers in Z. You can translate this. What it means is, this means that the negative 1 mode of V acting on the vacuum is just your original vector. And all non-negative modes act as 0 on the vacuum. So in particular, if you go back to our example, what it means is that our field X of Z is the field associated to the vector X negative 1 acting on the vacuum, in our case. In the Lie algebra.
Anything what we just said, that's X of Z.
So in our in our case of V being this vertex algebra associated to a Lie algebra, then the field that we've always discussed was the very special field corresponding to the vector x negative 1 acting on the vacuum. Right? And in particular, that goes then to your question. So this means the fields corresponding to Lie algebras that I have discussed were only very special fields of the complete vertex algebra.
And it's because you haven't told us what y is in that case.
And I haven't told you what y is, yeah.
I'm still trying to understand what's written there. So there's a capital V in the second line.
Yeah, that's so we have a vector
In
space.
the second line over there, is there a capital V or not?
Here, this is a capital V, yeah. So it says we take an
I mean, that's a small v, right?
yeah, we take an yeah.
And that's also
That's also a small v.
Yeah.
Capital V is a space. Capital V is a space.
yeah.
Yeah. Hmm?
So it just means it gives you v modulo that space.
Yeah.
So I guess strictly
okay,
speaking,
okay.
it should say belongs to,
Yeah, but
right?
Right,
in
yeah,
that
yeah,
case,
yeah.
Belongs to.
Absolutely, it's in the yes. So and right. So what it means is you can the action of this field acting on the vacuum gives you the original vector v plus a power series in z without a constant term and coefficients in b.
yeah, okay. This means now I understand.
Maybe I write it more. And this is equivalent to the third line.
Just to understand that in our case, that's like supposed to be what you've written there is telling us that there is a vertex algebra sitting on top of that particular V with the property that its Y,
Mm-hmm.
when applied to this particular
Yeah.
thing, equals this thing.
Exactly. And let me finish the definition and then I'll write down what you just said, maybe. So the translation operator, we wanted to act as a derivative. And if you think about it, in our Lie algebra case, this is very much like the derivation, in fact, minus the derivation of the Lie algebra. And then the most important property is that for any two fields, I can take the commutator and this commutator vanishes if multiplied by a sufficiently high power of z minus w. And this n depends on the choice of fields here.
And have we already assumed that all the, you wrote Vn where n is bigger than 0, do we already know that the V minus n's act on the vacuum by 0 in general? The negative.
No, there was the positive Vn that act as 0.
It's the, yeah, but so the other guy here, the y, has all kinds of powers, right?
Mm-hmm.
Yeah, okay, so, oh sorry, I'm just translating what it says above.
Yeah. So I should say, so first of all, I shouldn't have, yeah, but I should have written is, so this is equivalent. So this statement and this statement is equivalent, and so you were confused about this one, but this is of course nice and compact and tells you very nicely that you have a state-field correspondence, meaning you have a map that maps vectors to fields, and you also have a map that maps fields to vectors. Namely, what do I do is I act with my field on the vacuum and set z equal to 0. Right? If I set z equals to 0, this thing vanishes. I get my original vector back. And okay, so this property here is called locality, and it's the heart of the definition of a vertex algebra. It's the important thing. And I simply wanted to start motivating it with the whole Lie algebras so that this property doesn't come as such a huge surprise. We have seen it in these examples. This is also how people came up with it. In the 80s, affine Kac-Moody algebras, affine Lie algebras came up, and then people like Katz, they observed that the connection to vertex algebras and how this came about. Okay.
Locality, is that related to like relativistic locality? Or
No.
What kind of locality?
Yeah, you should, so it means fields are local in the sense that they commute except if they are very close to each other. That's how you should think about it. Right? So, and and in particular, you should think about it in this way if you keep this lemma in mind, which relates this to this one, right? Here we see this is the commutator of two local fields, namely the commutator vanishes everywhere except if Z and W are close. So of course, as a physicist, you probably would just like to smear this out and make this.
What was the question?
Why locality? What does the word locality refer to? Right, I should always repeat questions. Yeah. Okay.